In this section, I'm gonna talk about the airframe design. So, if you want to design a rocket that has given a given requirement, for example, reaching 10 kilometers at apogee, or 100, or whatever, the first questions that may pop up are, well, how long is that rocket going to have to be? Which diameter? How much propellant will I need? So, propellant, dimensions. The thing here is that it's, well, not easy to say. Why is that? Well, let's see why. So a rocket has liftoff mass. Okay, liftoff. It has propellant mass. And it has mass at burnout. So after burning out, mass is going to be the liftoff mass minus the propellant. Okay. So if you're familiar with the rocket equation, the total velocity that a rocket gains after burning its propellant is equal to the specific impulse of the motor. Okay, this is like how, let's say, how efficient our motor is, okay? Times just the gravity constant, this is 9.81, times the natural logarithm between the liftoff mass divided by the final mass of the rocket after burning out, okay? This is a very, very, very simplified equation, okay? We're just going to take a look at it just to see how, oops, let me get this off. Bye. This is a very simplified equation. We're just going to take a look at this just to see what's the problem with predicting, doing a rough prediction of how a rocket's going to have to be to comply with some requirements. So you're going to see it now because this is a mass ratio. Okay, Saturn I think defines it slightly differently. Okay, I think it's the inverse, but anyways, the thing is that this equation over here is the delta v, the velocity that the rocket gains, is super sensitive on the relationships between the masses. Okay, so maybe if we have a rocket that weighs, I don't know, 100 kilos, and if one design, you're always going to try to maximize the propellant mass, okay? Because if one design has, of these 100 kilos of takeoff mass, if one design has, I don't know, 20 kilos, and the other one has 80 kilos, so maybe the difference in height of these rockets, the height they're going to reach, maybe it's 5 times more. I don't know. It's very sensitive. What you have to know is that it's very sensitive. The apogee that the rocket reaches, respect to the masses. And well, guess what? It's really hard to know which dry masses. This is dry mass. Which dry masses you have in function of the propellant mass. So all the masses are pretty hard to predict. Okay, so let's see. Another thing is that the analytical solutions to the trajectory the rocket has are really simplified. This is super simplified. This is no gravity, no drag. This is extremely simplified. Okay, so we don't even use this for preliminary calculations. I just showed you this equation because it's probably the most it's the most famous rocket. It's called the rocket equation. Okay, so and I just showed you to explain the mass sensitivity to the velocity a rocket obtains. So maybe if this is a delta V and this is the mass ratio, well, I didn't show you what this is yet. So what I mean is that it's exponentially sensitive to the masses. Okay, but yeah, again, this is a really simplified model. There are other models, analytical solutions to the trajectory I'm gonna talk about, so you can predict predict what a rocket's gonna do. But still, all the analytical solutions are pretty bad to predict. Analytical solutions are really simplified. Okay. So maybe the best thing you could do is actually check an existing simulator. If you want to play around with, say, get the rough masses of what's your rocket going to be like. Maybe you want to check some existing trajectory simulator like OpenRocket. Okay. Before you program your own simulator, which is something you're gonna have to do if you want to, if you want to properly design your rocket and understand, its stability, the trajectory. So this is nice because it's really fast to, get a feeling of which rocket you're gonna need to reach a certain altitude. So I can't respond to all these questions just yet. So I can't tell you, like, more or less which dimensions, how much propellant you're gonna need to achieve a certain goal. But what I'm going to do is, I'm going to go through different bits and pieces of the design of the rocket. Okay, I'm going to start with the airframe, which is this section, and eventually you're going to be able to connect all the dots, and you're going to be able to respond yourself to that question. Okay, so I'm going to start with super basics. Maybe it's going to bore you. Okay, I'm going to start with basics. So if you're a bit familiar with, I don't know, the basics of this, it may bore you the first videos, but I'm gonna go up really quick, so don't sleep too much, and we're gonna see, how to in this section how to design the airframe, understand the trajectory a rocket's gonna have. We're gonna see the stability of the rocket. Okay, how to design stability. How to design a rocket that is stable when wind hits or whatever. I'm going also to go through how to design the fins, nose cone. I'm going to talk about heating of the nose cone. I'm going to talk about, how to, well, yeah, we're gonna see. We're gonna see all this and more. So yeah, get ready for this. Some sections are easier to understand just with basic maths. Some others, well, maybe you're gonna need. It's gonna help if you know some stuff, maybe control theory in terms. When I'm gonna talk about stability, maybe it's nice to know a bit about heat transfer when I talk about the heating of the nose cone. But still, I'm gonna point out where to look if you don't know these subjects yet. So yeah, let's go.